I appreciate all of you who are listening, who are also here at Case Western Reserve University. We are actually both live seminar and webinar going on. With that, I'd also like to thank Park Systems for this opportunity to give this important topic in the development of smart coatings. So I'm going to talk about nanostructured and functional layer-by-layer coatings. And before that, of course, I'd like to introduce our operation here at Case Western Reserve University. We are located at Cleveland, Ohio, at the University Circle, next to museums, Cleveland Clinic. And if you have a chance to visit us, you can do so when we're around, and I'd be happy to host you. Case has been around for since 1826, quite a distinguished list of former and present Nobel laureates associated with Case. Even the founder of Dow Chemicals is a graduate of Case. We are located at the 5th floor of the Macromolecular Science Engineering Building, and this is where our labs and our students work and do their research. Also, Case Western Reserve University is home of Pink Box, which is the additive rapid prototyping and advanced additive manufacturing facility that we take advantage of, but primarily available for undergraduate students to use. I will be talking at the end of this lecture about our CLIPS Center. It's a National Science Foundation funded STC that we have used in our group in particular to create smart coatings and different types of nanostructured polymer extruded layers and ultrathin films. Although it's much more than that, it has been going on for the last 10 years. We are also home to PetroCase, which is polymers for energy and transformative research in oil and gas. What we do here is we try to use the best, smart, and high-performance materials to solve some of the pressing needs of the oil and gas industry. I know, and we all enjoy the current gasoline prices, low energy prices, gas energy, etc. But believe me, this is a very cyclical industry. It can go up and down, but the problems do not go away. After all, since we are a research group, we do a lot of research at interfaces, chemistry, reactions, different types of smart and nanomaterials that can be nanostructured, and the applications of innovative analytical methods is very important for us. And actually, because of this breadth and work on interfaces, we have since graduated 28 PhDs in my research group. On the other hand, we are very much attuned to what industry does. So what we do is we take the best of the basic platforms that are developed in the university, and we translate this or do translational research for what things can be applied towards smart technologies, product development, and solving some of the most important or critical problems in industry. It's all about communicating, and it's all about translational research and what it means to do innovation instead of inventing. What we are after is essentially helping you or working with industry, helping them meet the requirements or market demand of their products, services, or research. So we try to create these bridges that allow us to understand the market needs and how we can work with companies to take the basic and best technologies coming out from university. So it's all about increasing efficiency, finding the performance cost ratio, and finding the demands, converting it from wants to actual needs. So let's start by looking at a coating and a layer. A coating has several functions. An important function, of course, is preventing the environment from affecting or attacking the bulk material. On the other hand, a coating is also a packaging proposition. That is, it protects the environment from the effects of the bulk material or seepage or leakage. So in other words, the functionality that you build to the coating, whether we're talking about millimeters to nanometers, is very important for that type of proposition. Whether it's a barrier material, a protective coating, a controlled release coating, or stimuli responsive material. Such that when we look at these different types of consumer proposition or even biomedically relevant interfaces, we want to find or define structure property relationship that allow us to understand different hierarchical levels of complexity or relationship, starting from the molecular, nanomolar, mesoscopic, microscopic, all the way to macroscopic. And I have, of course, stories to tell in each of these projects that we have done, from super hydrophobic coatings to OLED materials to different types of anti-scratch coatings, but I'll let the story evolve as we go through the different projects that we've been doing in our lab. So what are nanostructured materials or nanomaterials in general? The relevance that we get from a nanomaterial is not only based on its size and scale, but the way it is structured. Nanostructuring can come from both ways. It can be a top-to-bottom approach or bottom-up approach. A bottom-up approach means we need nano-building blocks that can be assembled, self-assembly or directed assembly into a particular structure that results in function. On the other hand, a bulk material can be lithographically or non-lithographically accessed to provide the structure. In other words, you cannot distinguish the structuring from the function of the nanomaterial or the lithograph pattern. Now, a polymer to us is not just plastic, but it's a true nanomaterial in the sense that one can apply this towards ordering as films, ultrathin films, individual polymer brushes, membranes, structured hybrid materials. On the other hand, a polymer as well can also be an integral part of a network or solution or a viscosity modifier that interacts with other nanomaterials in terms of Pickering interactions, agglomeration, or controlled cross-linking. Hence, together with nanomaterials such as quantum dots, colloidal particles from silica, gold, graphene, carbon nanotubes, polymers have a very important place in nanostructuring and coatings as well. So let's try to define the innovation we want to do with surface engineered products. A surface engineered product can be approached from a variety of directions. Important, for example, is we want to add high value added functionality, or we want to improve material usage or efficiency by which we use different types of additives, either make these additives more effective or less costly. Another is to provide performance that is, of course, not possible with thicker films or bulk materials. Hence, we are dealing with increased and improved performance and perhaps reduced costs that will be attractive to the final end user. Coatings, therefore, offer an enormous potential to do the following. It can create an entirely new product, a solution to a previously unsolved problem, improve the functionality of an existing product. It can be used to prepare new nanocomposite materials, conserve rare additives or costly materials, and perhaps sustainability engineering. What is a basic coating procedure? First is we depend on a molecular design or a formulation that can be optimized such that when properly layered, it will provide function. Then we have to define that delivery method, whether it's spraying, painting, or use of different nanostructured procedures. And then finally, we need to consider the substrate itself, the deposition and ordering that is achieved once it goes to the substrate. Now that can mean a flat surface, or it can even mean a particle surface. Now, going over the type of coatings that we generally talk about, when we talk about paint, different types of do-it-yourself, other types of coatings prepared from either formulations consisting of waterborne paint or solvent-based paint. Most of these are labeled as architectural coatings. And then we have industrial and light industrial coatings that are mainly protective in function, as well as different types of direct-to-metal coatings. Another is finishing coatings. That means these are applied to the product even before it leaves the factory, such the case of automotive coating. Specialty purpose coatings are meant to be field applied, or they can be factory applied, and their function is towards high performance or the use of different types of formulations or coating methods that are very important barrier functions. How do we divide these special purpose coatings? This can be further divided into segments including high performance, automotive refinishing, industrial maintenance, marine coatings. This can be applied either by powder, heat, UV curing, or spray thermal procedures. We are actually going to talk a lot about nanostructuring, and therefore you will hear today about methods utilizing physical or chemical vapor deposition methods and layer-by-layer coatings in particular, as well as the introduction of polymer melt extruded films. Along with this type of methods, one can look at plasma deposition, deep-coated coatings, Langmuir-Blodgett deposition, atomic layer deposition as auxiliary to other types of smart and nanostructured coating procedures. Of course, we have utilized UV cured coating as well. That means the chemistry is involved towards curing the polymer or the coating towards functionality. So we find multilayers in everything. In coatings especially, this can come with different function. For example, in hard floor coatings, we could be talking about different types of abrasion resistance, different slip resistance. Automotive coatings, we can be looking at a clear coat, a base coat, a primer, and then the addition of additional protective coatings based on anti-corrosion properties. For steel coil coatings, for example, we can be talking about a zinc or anodizing coating that provides a galvanic protection, together with chromates, and then finally primer and a top coating. All of it is meant to produce a robust coil coating or a metal sheet that can be transported and rolled. Now, what you can see in this bulk, what I call bulk coatings, the common ingredient, of course, is a primer layer or even an additional protective and adhesion layer that makes it a surface amenable to the addition of other functional coatings. In other words, that adhesion layer is very important because it sets the stability and functionality of each succeeding layer. Now, as we go to other types of coatings, we could be talking about anti-reflection coatings. Anti-reflection coating means you have very high transmission, and usually this is done by matching the refractive index and the layer thickness of the succeeding layers. Anti-reflection coatings are in general transparent coatings, so that means they're very important in things like smartphones, display devices, and different types of optical applications. Usually we use the quarter wavelength rule, in which the thickness and the refractive index between air and the material, it could be an organic material, is an intermediate number. With dielectric materials, we're dealing with capacitance. So a typical dielectric will have a sandwich design based on an electric or dielectric interface where the dielectric or insulating material is between these two electrodes, and therefore you have a gap function. Other coatings could be smart coatings that resist oil or resist water. In this schematic layer-by-layer composite coating, which is actually made up of silica particles together with polyelectrolytes, in which the topmost layer is a fluorinated surfactant. This particular layer-by-layer, if not layer-by-layer, self-assembled monolayer device or substrate is meant to hate oil, and that's why the term super oleophobic. Other types of multilayers can be prepared. For example, a method called atomic layer deposition involves the chemical reaction of succeeding layers in which the reaction can be based or controlled as monolayers of molecules that are reacted or adsorbed, chemisorbed with each succeeding layers. Thus, you can make or incorporate various designs or what we call supramolecular assemblies of different sequences of polymers or even chemical bonds that are introduced with techniques based on chemical vapor deposition as well. Two-dimensional lattice materials or 2D nanomaterials have the function of being able to make layered systems based on the geometry and the flatness of the adsorbed material towards higher function. Of course, a naturally two-dimensionally layered material will be your graphene that can be derived from graphite. In biology, of course, we can be dealing with bilayers or different types of bacterial proteins. In this case, S layers, a protein that's highly structured, which is derived from bacterial protein, glycoproteins, for example, that can be prepared as a multi-layer, highly ordered or patterned film on surfaces. So let's talk about layer-by-layer ultra-thin film nanocoating. So as I mentioned, since we find layered systems all the way from what we call bulk coatings to nanolayers, let's try to identify what layer-by-layer coatings are. I could be talking about inorganic, sol gel, I could be talking about ALD, but I chose to focus on what we call nanostructured organic and polymer layer-by-layer ultra-thin films. Now, as you can see in this diagram, chemisorption, and that means reactions that are based on the self-assembly or directed assembly of molecules that adsorb, whether it be amphiphiles or reactive silanes that can be ordered and deposited on a layer-by-layer basis, will end up to be a nanostructured film. Even back in the 1930s, people have appreciated what they call the Langmuir-Blodgett or Langmuir-Blodgett-Kuhn method. In this case, the main ingredient would be surfactants that are deposited at the air-water interface and involves that of a substrate that can be dipped vertically or even horizontally using what we call the Langmuir-Schaefer approach to form multi-layers. I'll be talking a lot today about layer-by-layer films, and this can be accessed through deposition of water-soluble polyelectrolytes or reactants where you can incorporate proteins, nanoparticles, different types of macromolecules and small molecules through this simple assembly approach. Another is that polymer multilayers can be accessed through deposition. This can be done again by CVD or PVD, physical vapor deposition, where you vaporize or sublime the ingredients on a layer-by-layer fashion to a substrate that is either cooled or activated with the presence of an ionic charge. Actually, we pioneered methods involving electrodeposition or electropatterning, even on a layer-by-layer basis, as well as the grafting of polymers on surfaces or what we call polymer brushes. Actually, when we talk about nanostructured layers, one can, of course, graft individual polymers on surfaces, either flat surfaces or patterns or particles in three different modes. One is what we call a grafting onto method that involves a preformed polymer that can be chemically or physically adsorbed and then grafted as a polymer brush on a surface. Another is you can do the polymerization right at the surface where the surface is populated with adsorbed monomers. Lastly, one can also prepare surfaces based on surface-initiated polymerization where the initiator is grafted on the surface and then you can grow a polymer brush. In this case, the grafted polymer ends up to have a higher grafting density because the polymer is directly grown from the surface through a surface-initiated polymerization process. And we have demonstrated this in a number of layers, including layer-by-layer coatings, where we can then delaminate the film and result in freestanding polymer films with a combination of both grafted polymer and layer-by-layer polyelectrolyte deposited materials. As you can see here, one can translate this type of chemistry towards particle surfaces as well. Hence, you can produce different types of colloids or colloidal particles with hollow shell, coarse shell, multi-shell geometries that can be prepared through different types of polymerization mechanisms. One of the more important substrates is, of course, particulate clay, which can be found in paints, composites, nanocomposites, drilling fluids. In this case, we pioneered a lot of work in grafting different types of polymerization methods on the intergalleries of clay, both to delaminate them and functionalize them as nanocomposite clays. So let's talk more about nanostructured layer-by-layer self-assembly. Although this can be demonstrated again with a number of chemi-sorption and multi-layer vapor deposition, plasma deposition method, I chose to highlight nanostructuring using polyelectrolyte assembly from aqueous-based solution. This is so easy in that high school students have long used this method to prepare nanostructured films, where all it takes is a solution of two oppositely charged polyelectrolytes that can be alternately deposited on a substrate and then grown towards different types of thicknesses or layer assemblies. In this case, the electrostatic charge attraction between a negatively charged polyelectrolyte and a positively charged polyelectrolyte allows the buildup of layers essentially through equilibrium ion exchange, resulting in the buildup of these truly nanostructured films. Now, this can be done on particles as well, which can result in these core shell particles, and many procedures have actually been developed to digest or remove the core to end up with what we call hollow shell particles. This type of coating is not only done by dip coating, but can also be done by spraying, spin casting, resulting in freestanding and swelling films. So for example, if you alternately spray solutions of those two polyelectrolytes, you can easily build up this substrate with the number of layers directly proportional to the number of spray treatments you did. On the other hand, one can also grow these films by alternately depositing it on a substrate and then using spin coating to produce thin films. The number of layers, again, will be proportional to the thickness obtained, and by delaminating methods or creation of sacrificial layers, one can isolate what we call freestanding films. Here is a good picture of how the material that you deposit results in different functions, as simple as pH change or even playing around with the use of polyelectrolyte concentration as well as charge density based on the incorporation of salt. Here you can see that swelling can be done or performed with different types of materials or layers. Potential applications of these films could be LED devices, anti-reflection coatings, fire-resistant coatings, gas and ion transport membranes, antimicrobial coatings, controlled release coatings, and so on. Many groups have done this work. This was pioneered even way back in the 1990s. Our group actually did a lot of work with these different types of functions more than 10 years ago and still continue to do so with different types of materials and the use of surface-sensitive analytical and microscopic methods to probe their function and properties. So for example, one of the materials that we focused on early is the use of azobenzene polyelectrolytes and dyes to create holographically patternable and tunable based on the photoisomerization gratings. So in this case, the polymer material, the active component will be polyelectrolytes with azobenzene dyes that can be photo-patterned or photo-aligned using holographic procedures. Another type of interaction could be the incorporation of catalytic or antimicrobial type of additives with these coatings. Here's an example of silver nanoparticles that can be formed inside multilayers of polyelectrolytes by reduction, resulting in nanoparticulate silver that can be released or even coated as electroplated materials on this type of nanostructured layer films. When we talk about sol gel coatings, we usually refer to the use of alkoxides, metal alkoxide precursors that can be introduced by solution methods and thermal processing to result in mesoporous aerogel, hydrogel, and serogel films. On the other hand, this type of procedure is essentially a hydrolysis procedure followed by condensation that can result in glasses or cross-linked silanes or silicones. Actually, you can incorporate other types of organic materials or even polymers to mediate the cross-linking as well as the incorporation of different metal oxides based on alumina, zirconia, titania to this type of coatings. Now, this type of coatings can be made on bulk, but more interestingly, it can be done on surfaces as well. This is an example of layer-by-layer surface solder processing in which the alkoxysilane or metal alkoxysilanes can be introduced one layer at a time on a hydroxyl surface, followed by washing, which then generates a hydroxyl group functional surface, which can then be amenable for further reaction with the corresponding metal oxides. And thus you produce surface sol gel glasses or different types of surface sol gel ordered layers that can be used for a variety of optical, catalytic, and functional applications. Nanostructured coatings can also be prepared by physical vapor deposition methods. That means that the source material has to be heated under vacuum, and that's very important. Using high vacuum, one can approach values up to 10 to the minus 7th torr, and this means that you will need lower temperature to vaporize the material. Now, this can be effectively done with metals, hence metal vapor deposition methods, as well as polymers or organic materials. So in this case, as you vaporize the material from its source, it then deposits or sublimes on a substrate surface of your choosing. You can manipulate the electrostatic charge, the ion charge, the temperature of the substrate to control this process. Hence, this diagram shows that our group actually in cooperation with the Usui group at the Tokyo University of Agriculture and Technology pioneered a number of deposition methods for making polymer films, either through the direct vaporization of a oligomer from a source or the direct polymerization of two monomers to a substrate from two sources, or the application of a activation method such as an electric field or UV field to result in a polymer film. And then finally, we can actually evaporate the monomer, in which the initiator is located at the substrate, to result in a surface-initiated polymerization method by vapor deposition. So let's talk a little more about devices, electronic devices, solid-state devices. We could be talking about solar cells, actuators, LED devices, sensors. A lot of this means that for the active material, if it is based on a polymer, has to have the function of charge carrier mobility or pi electron delocalization. In other words, the polymer has to be pi conjugated, electrically conducting, or even nonlinear optically active. We developed more than 15 years ago a method to deposit different types of polymers by electropolymerization, in which the resulting material is actually electrically and semiconducting based on electropolymerization methods such as cyclic voltammetry or potentiostatic deposition methods. The result is the formation of robust films that can actually function to improve the device or the preparation method for making that device into a bulk heterojunction cell or even a light-emitting diode. For example, we utilize this method to prepare a very thin layer of a whole transport material based on polyvinyl carbazole, which can then be prepared on an ITO substrate. And depending on the oxidation state of the PVK, we can tune the turn-on voltage of a device which consists of an active electroluminescent polymer material such as polyfluorine. Now, this demonstrated the importance of selective structuring, not only in terms of controlling the roughness, but also the whole transport property of this supporting material to prepare a more efficient device. Actually, together with for preparation of layers, the application of patterning is very important. In many devices where the pattern plays an important role in either a photonic function or sensor function, this can be accessed through a number of methods. As you can see here, the hierarchy goes from lithographic, non-lithographic methods, or the application directly of the material by deep pen nanolithography and the use of E-beam lithography to access very, very small features. The features we're talking about these days when it comes to microprocessors are in the range of tens to 15 nanometer. And that is somewhat the limit of many methods following Moore's law, where we can incorporate as much transistors in a given area. About 10 years ago, more than 10 years ago, we experimented on the use of electrodeposition methods to make micro patterns of LED materials as shown here, that is derived from a modified polyfluorine which can be electrodeposited on a self-assembled and microcontact printed circular patterns. This type of patterning enables the formation of a blue light emitting diode, or I would say micro LED, based on the clear or high resolution of patterned circles in this area, where the use of the precursor method was very important. And this was done either by using a cyclic voltammetry or a potentiostatic method. Now from micro, we then access nano. And nano patterning for us involved the use of AFM, atomic force microscopy, again a very important tool, not only for imaging but for patterning as well, where the active material was actually present on the film itself prior to the patterning. With this method, we were able to access features, 100, sub-100 nanometer features, where we have demonstrated these nanostructured films can be prepared using the AFM tip with a bias voltage that then results in electropolymerization of these patterns. These particular patterns can be applied towards the preparation of sensors as well as memory devices. Now, just to demonstrate how these materials and methods are integrated, especially with layer-by-layer systems, let me start then with this material that we prepared based on a polycarbazole. The polycarbazole, as I mentioned earlier, is important for whole transport and hence can be equally applied towards different solid-state devices based on LED. It can also be electropolymerized based on the oxidative cross-linking or reaction between these carbazole units. So in this case, I asked Cheng Yu, my student, to prepare a positively charged polyelectrolyte with a particle, with a carbazole unit, and then a negatively charged polyelectrolyte with a carbazole unit. These two polymers can then be built using the layer-by-layer method I mentioned earlier. And the result is we can track this layer buildup using UV spectroscopy. So as shown here, as we deposit more layers alternating between these two polyelectrolytes, it resulted in increasing absorption. We then electropolymerize this polymer once the film has been built up to enable us to access the formation of polyvinyl carbazole. Now, this was a joint project between my two students, Cheng Yu Wang, who did the synthesis and the characterization of the polyelectrolyte, and Go Chan, a PhD student who did most of the patterning methods. So I asked Go Chan to prepare these patterns. These are patterns based on the use of, again, the bias voltage tip to produce patterns based on lines, different types of surface-related structures, test patterns where we evaluated the thickness performance, thickness as well as the dimensionality or width of the patterns. Now, one night, I asked Gotchan and about to leave to show me his recent result. And he showed me a heart-shaped pattern, as shown here below, that surprised me. I actually asked him, why are you making heart shapes? We are not supposed to do this type of patterns. We're a scientific lab. And he said he liked it. And okay, I said, you like it? So, all right. And then 2 weeks later, they came to me and said, okay, we have a temporary setback here. Let's try to restart it. Okay. So we discussed the matter, and he showed me this film. So 2 weeks later, this is what happened. They both came to me and said they were getting married. And not only were they getting married, their work became cover page for Macromolecules. So I can definitely tell there's lab in my lab. All right. So from nanopatterning, we've tried another patterning method called colloidal sphere nanosphere assembly, or patterning. What it is we take colloidal particles and make them two-dimensional layers, hexagonally packed as shown here. And essentially, we use them as templates for electrodeposition. So for example, in this first paper that we published, where we use polypyrrole as electrodeposited material, it resulted in the formation of honeycomb bee structures, half dome and full dome, and we can even remove the full dome and half dome structures to result in capsules as shown here. And this patterning method, which is clearly highlighted here by AFM, shows that these conducting polymer layers essentially can be templated by the original colloidal structure to produce these arrays, and this was synthesized by electropolymerization by cyclic voltammetry as shown here. We can actually do more chemistry on these layers. We can attach ATRP initiators inside those layers in the middle part and then grow a polymer brush by ATRP. And the resulting difference in morphology is clearly shown here between the colloidal, between the pattern arrays without the polymer brush and with the polymer brush. And actually, again, AFM was very important in the characterization method because here we utilize current sensing or conducting AFM to distinguish that indeed the polymer pattern array consisted of the more conducting, electrically conducting or electroactive polymer material compared to the polymer brush, which showed a false green color as shown in this micrograph. More recently, we actually utilized this method to prepare virus nanoparticle assemblies that can be deposited in these arrays. CPMV or cowpea mosaic viruses are harmless. They're not the ones that cause Ebola or SARS or AIDS. They're the ones that we harvest from plants. And they're true nanomaterials as well. As shown here, we can deposit them on these conducting polymer arrays and they reside on the ridges, as well as enable us to remove freestanding films as shown in this AFM micrograph, where we can isolate them as one layer or two layers electrostatically adsorb on these patterns. Now, the final part of my talk is actually about CLIPS. CLIPS means Center for Layered Polymeric Systems. It's an NSF center or science technology center. What this is that we are able to take two immiscible polymers or two polymers that have a very big difference in their chi interaction parameter and then melt co-extrude them using this device. So from the polystyrene to PMMA feedstock, we first deposit them on top of each other as the first iteration, and then we separate the two films and then stack them against each other to form a quadruple layer. We repeat the process n number of times or by the number of multipliers such that at the end of the extrusion process we end up with a multi-layer film. So as you can see in this diagram, what we achieve is essentially a nanostructured film that can either be used as a freestanding film, foil, or coating, where the layers are clearly separated as alternating layers of immiscible polymers. If you do this process enough, you actually reach the limit of thickness and interaction such that they become indistinguishable. In other words, we can reach layers thickness of the order of 10 nanometers or less, where we can then separate each alternating material basically through extrusion. So I actually had one of the important platforms in this center. In our platform, we are actually interested in different methods of templating, functionalizing, doing chemical reactions, patterning of this type of films. That means we can incorporate controlled release systems, surface modification, different types of fiber, nanofiber access, or even patterning methods. And I'll just show you some of the projects that we do. One is we're very interested in the extrusion of two polymer films in which the functionality can be added to one layer that can result in guest host systems or controlled release systems, including drugs, dyes, different types of actives that can be incorporated with one layer and the other layer serving as a protective layer. By controlling the number of iterations and the amount of material we load each of these layers, we are able to perhaps control, and we've demonstrated then controlled release properties. Another property is that we can actually isolate each of these layers and produce sheets or nanosheets. The dimension is basically from the starting point of the original film and then delaminating them into individual sheets that can be isolated either by dissolution or direct delamination, even the use of a scotch tape, such as how it was done first with graphite producing graphene. In another project, we demonstrated that these layers can be made functional on the top surface or pattern with methods such as photografting or the incorporation of photoactive materials. Benzophenone group, in this case, it resulted in the grafting of a polymer brush from an ATRP base initiator. We then deposited this on surfaces or pattern surfaces, resulting in different types of pattern and polymer brush morphologies. And the paper actually has been published in Macromolecular Science and Engineering. Another is that we can use lithographic and non-lithographic patterning methods to take essentially these multi-layer films. In this case, we demonstrated the use of capillary force lithography to produce these interesting patterns which can have both wetting control as well as optical function or band gap properties that can be introduced together with the differentiated refractive index materials. For example, the SEM micrograph as shown here shows the type of patterns we can incorporate on these films or the corresponding change in wetting behavior as we introduce these interfacial patterns. So believe it or not, the R is almost done. I'm basically going to conclude this talk by my perspectives on the future of coatings. There's going to be increased molecular and macromolecular design. That means brush up on your chemistry. Formulations, high throughput design can give multifunctionality. And of course, we can see here a convergence of function from a bottom-up approach or from nanoscopic to microscopic. On the other hand, there's a convergence of design from a top-to-bottom approach or from macroscopic to nanoscopic. Essentially, we've utilized a number of surface-sensitive analytical methods, including IR, XPS, but then what I highlighted in this talk are the number of times and the importance of utilizing atomic force microscopy in all these nanostructuring methods. A lot of things can be derived from nature. Superhydrophobic effect is a very good example. We inspire to solve problems in industry, and therefore cost-effective and high-performance materials is always of importance for commercial translation. And hopefully all of us here, including the rest of the audience, will take time to innovate. So with that, I'd like to thank you for listening, and I'll be happy to take some questions both live and online. Thank you.
Wonderful. Thank you very much, Professor, for the enlightened talk, and also for retelling the nanopattern lines and love chemistry story. That's still one of my favorites in this series so far. As the professor has said, we have reached the end of the talk, and we will now be doing the Q&A session. So there is a question in queue. While I relay it to the professor, if you have any questions online for those who are attending via the webinar, please send them in by typing them into the questions module, and again, we'll be answering them sequentially. For the offline Q&A, I suppose we can do that after the session has disconnected, so thanks again to those in the in-person audience. Our first question reads, how important is it to modify the silicon wafer substrate before coating?
Very good question, if not a universal one. Believe it or not, many coating applications, and I'm talking about paint bulk coatings, industrial coatings, fail because of lack of surface preparation. In other words, before you use that expensive high-performance coating or paint from top paint from Sherwin-Williams, if you do not prepare the surface very well with a standardized cleaning method, preparation method, you're setting it up for failure. The same with functionalization of silicon wafer. So the silicon wafer has a native oxide layer, and of course sometimes during transport, storage, it can have other types of contamination, including dust. It's always wise to use a type of surfactant or even plasma cleaning procedure to create a fresh oxide layer prior to self-assembly. So in that case, any type of coating procedure is highly dependent on how the surface was prepared in the first place.
Great. Our next question reads, who are some of the leaders in lithography, and why do you consider them leaders in that particular line of study?
Very hard to say without being political here. I would simply divide them between lithographic and non-lithographic methods. Of course, when we talk about lithography, we are talking about people who've contributed much with photolithography, photomasking, or even the use of direct e-beam lithography. On the other hand, the non-lithographic methods, which I like very much because of its simplicity, many things we can associate with self-assembled monolayers and patterning and use of stamping goes all the way to Whiteside's, his former students as well, and of course the marriage of micro contact printing and self-assembly. Of course, would like to acknowledge Paula Hammond. But other types of printing, non-lithographic methods, embossing, could equally be applied to things like capillary force lithography or flash lithography, S-fill methods. I, of course, think of Grant Wilson, who did a lot of work on S-fill. So, without being political, I could simply divide the pioneers between lithographic and non-lithographic methods for patterning.
Great. Our next question here reads, which method of nano patterning do you find to be the most promising for scaling up?
Yeah, good question. Anything that involves a non-lithographic method, that means a variant of stamping or embossing that can be done in a roll-to-roll fashion, can have a higher chances for scalability and cost reduction. So I would think of techniques like what I just demonstrated, capillary force lithography, as one of the easier methods. Another is based on a material like a polymer which can be heated above its glass transition temperature and simply embossed or printed. In this case, you retain the pattern upon cooling of the polymer material. Of course, it also depends on the value and the cost of the final product. When we talk about microprocessors, indeed it takes a lot of time, even a fabrication facility that can cost billions, but the end result will be chips or products that can go to universally to a number of devices we use every day, such as this notebook computer or smartphones. And so if we talk about scalability, if we talk about cost, eventually it depends on what is the value it adds to the process, and let's say how much the customer is willing to pay for. So it can be a very expensive process, but very integral to the function, or it can be a cheap or inexpensive process, and your product is not that expensive, then those two types of proposition work very well.
All right. Well, so far I believe we have only a couple minutes left in the hour allotted to us. And that seems to be the end of the questions that have queued up so far. So I'll give a couple more moments to people who are still finishing typing to do so and send them in. In the time remaining, I wanted to point out, for those of you who have not joined us before, this is your first webinar that you've attended in this series. I'd like to point you to our website, parcafm.com, AFM as in atomic force microscopy. On parcafm.com, there is a repository of all of the recordings of previous webinar sessions that we've done with Professor Vincula and other speakers as well. Professor Lane Baker from Indiana University also comes to mind. And those are available to watch at will. You can also see them on the Park Systems AFM YouTube channel. So all of the previous 12 or so talks that we've done with Professor Vincula are there to watch for posterity if you want to review anything that you feel like you may have missed. And here the professor has put up his title slide again. If you have any questions that have come up, maybe sometime after the session, you can reach him at rca41@case.edu. And if you have any questions about the atomic force microscopy systems that have been used to do some of the characterization scanning and imaging in the presentation, you can find out more about that at our website, again, parcafm.com. Next month, we will be returning with Professor Vincula for another entry in this series. And I believe we're scheduled to look at, again, coatings, but this time we're taking a closer look at superhydrophobic coatings, which was mentioned here in this presentation. And then our final announcement is that next month, Professor Lane Baker will be returning to do his series once again. There was a long postponement, but he is returning with his electrochemistry series as well next month. And you can register for both of those shortly on parcafm.com. I believe Professor Vincula's next session is already up there for registration. So, no other questions have come up in the interim. I believe I've covered everything that I wanted to hear. Thank you again for everyone who has attended online as well as in person. And Professor, do you have any closing thoughts?
Well, again, I'd like to thank you, Gerald, for smartly handling our session. And of course, I'd like to thank everyone, both live and you at the audience at the webinar, for being part of our series and taking time. And like what Gerald said, if you need to contact me, you can email me at rca41@case.edu. And if you happen to be at CASE, let me know. We'll be happy to welcome you and give you a good tour. So thank you, everyone. Good night, good morning, or good afternoon.
All right. Thank you, everybody, and we'll see you again soon. Take care.